let's start. So, hello everyone. I'm Corentin Wallez from Google. I'm tech lead of WebGPU at Google and co-chair of the respective W3C working group. And with my friend François today, we're going to talk about, you guessed it, WebGPU.
So tell us, Corentin, what is this thing called WebGPU?
Well, I'm very glad you asked, François, and the clicker is not working. Yes, WebGPU is a lot of things, but the first and foremost, it's a new API for the web, which exposes modern GPU hardware access to web pages for both rendering and computations on a GPU. It's similar to Direct3D, Vulkan, and Metal in that respect.
What did you say? Like, I'm sure we've lost at least one person here, right? So, like, what is this Vulkan thing you mentioned? I guess it's not some kind of Roman god, right?
Right, I'm glad you asked again. Thank you, François. Vulkan is an API exposed by your operating system that lets applications talk to your GPU natively on Linux, Android, and Chrome OS. And Direct3D is the same for Windows, and you have Metal on Apple devices.
Okay, so WebGPU exposes modern GPU hardware access to the web for both rendering and computation operation on the GPU. It really sounds similar to WebGL, the API web developer use today to draw 3D things on the web. So, like, why do we have a new API then?
You're right. WebGL seems like it fills some of that purpose, but today we need more than WebGL, while at the same time that API shows its age. So WebGPU offers access to more advanced GPU features and provides first-class support for general computations on the GPU.
It's still not clear, right? So, like, can we share some real example of what we can do with WebGPU so that we can at least have a sense of what is possible with those modern hardware capabilities?
Okay, so what you want to see is pretty pixels, right?
Yep.
Okay, great. So we're going to go to demos. Yay. So the first demo here is, and I'm going to need the notes there, is a demo that doesn't really have pretty pixels, but it is a large language model that's running in the browser. So in this case, it's going to be Llama 2. And it's running using WebGPU computators directly on the computer. So we can ask questions or...
Introduce yourself, I guess.
Yeah, I'm introducing myself. So here it's loading the model in WebGPU. Luckily, I have all the weights and stuff in the browser cache. Otherwise, like 4 gigabytes of data, that would be a bit too much for the Wi-Fi here. And please, yes. Okay, so it's a... That was a very short answer compared to the ones we had. Anyways, so we can ask like some questions. What do you know about DevOps? And we'll get some information like, oh, DevOps is in Belgium, yay. So what's nice here is this can run on the web thanks to computators, and we're going to talk a lot more about that later. And this demo was published by WebGPU enthusiasts only 2 days after Llama 2 was released, so it's just it was really fast to get there. This second demo uses WebGPU both for rendering and computation. So this is a simulation of particles gravitating some black hole. And what's interesting is that it uses both Lagrangian and Eulerian fluid simulation. That would not be possible without the use of computators. So again, here it's the computator functionality that unlocks this type of things on the web. And the final one shows the Play Canvas kind of web game engine. And so this demo uses compute shaders and compute shader-like functionality to make rendering more efficient, and so we can do fancier rendering with the same computations. So in this case, what's very expensive is the computations of the lights, because they're real lights, and there's just a lot of them bouncing everywhere. So that was it for the demos.
So those demos look great indeed, thank you. But before we dive into how WebGPU works, let's zoom out a bit and start from the beginning, when it all started. So thank you, I'm glad. So 6 years ago, companies like Google, Apple, Intel, Microsoft, and Mozilla got together and realized that we were getting to the limits of WebGL. And they needed to decide what's next. So they've created a community group at the W3C to collaborate on designing the successor of WebGL. And
Sorry.
oh. And the easy solution would be to take an existing graphics API like OpenGL, Metal, D3D12, or Vulkan. And I think you can see where we're going there, right? There were too many APIs to choose from, yet none of them was a perfect fit for the web. And that's how WebGPU was born. That process took 6 years, with more than 100 contributors from all around the world, 2,000 commits, and 3,000 open issues on GitHub for one specification that everybody would agree on. This came with multiple heated debates, of course. For example, the choice of a shading language.
But François, what's a shading language?
I'm glad you asked, Corentin. While WebGPU is the API that allows you to organize commands you send to the GPU, a shading language is a programming language specifically designed to write shaders. And shaders are basically small programs that are executed in parallel on the GPU. And we had a bunch of existing shading languages to choose from, like GLSL, HLSL, MSL, SPIR-V, yet none of them was a perfect fit for the web. And you guessed it, Wixel, a new shading language for the web, was born.
Okay, so that's great for history, but what's the current status now?
WebGPU shipped a few months ago in Chrome browser on Chrome OS, macOS, and Windows. And you can expect to see WebGPU on Chrome for Android in Linux very soon. Note that Firefox and Safari engineers are implementing WebGPU as we speak in their respective browsers. So that's how WebGPU started. Now, let me give you a quick tour of what makes WebGPU great not only for graphics, but also for machine learning, scientific, and high-performance computing. But before we move forward, let's take a brief step back in time. 25 years ago, the GPU was used for graphics only to render beautiful triangles on the screen. 15 years ago, people suddenly realized that the GPU was also excellent for parallel computation and started using it for scientific computing. Finally, 5 years ago, the boom in AI and cryptocurrency mining was made possible by the GPU's efficiency for this type of massively parallel computation. And today, WebGL only explores the triangle drawing functionalities of GPUs, not their modern general-purpose parallel computation capabilities. WebGPU enabled these capabilities through the use of compute shaders. Remember the demos? They heavily used compute shaders. WebGL has a lot of global state, as you can see in this diagram. And it is very easy, and maybe too easy, to forget to change a global setting in WebGL. And this is still a major source of error for developers. Unlike WebGL, WebGPU is a stateless API and does not maintain a global state. Instead, it used the concept of a pipeline to encapsulate all of the rendering state of WebGL that was global in WebGL. WebGL also used command encoders to batch commands together and execute them in the order that they were recorded.
To be clear, I think you meant WebGPU. WebGPU uses command encoders.
What did you say?
WebGL. It's okay.
Do you want me to start again? Nope. 30 years ago, the state machine design of WebGL was a good choice. But since then, composability of software has become much more important. WebGPU, and not WebGL, it is a stateless API that improves on WebGL state machine design, making it easier to compose libraries and middleware. Nowadays, most of the video conferencing tools we use are built on web technologies, and video processing is most efficient when using the GPU. This is because web technologies are widely supported across a variety of devices and platforms, and GPU can perform video processing operations much faster than CPUs. This code, for instance, shows you how easy it is in JavaScript to import a video frame object as an external texture you can use in WebGPU. And for this reason, we made it both easy and efficient to use WebGPU for videos, with the goal to add more visual effect and save battery when doing video conferencing. For example, WebGPU can be used to implement real-time background removal, noise reduction, and image enhancement. When doing some GPU programming, it is a common joke that you get the dreaded black screen and you have no idea why. Without actionable error messages, it is extremely hard to know what to fix. In WebGPU, we ensure that every time something goes wrong, we get a very explicit error message. And that's obviously only one aspect of ergonomics. But more importantly, we made sure that WebGPU is easy to use with a minimal amount of boilerplate code and few foot guns.
Okay, François, enough blah blah about the API. Can we get some code now?
Okay, I'm glad you asked. This code is all you need to get a red triangle on screen. And this is kind of the hello world for graphics API, by the way. If you've done some graphics programming before, you know that 50 lines of code to draw a red triangle with a low-level graphics API is extremely short and to the point. So let me break it down a bit for you. Accessing the GPU is quite easy with those 2 lines. The first line gives you a GPU adapter. You can think of the adapter as the physical graphics card on the machine. It can be either on the same chip as the CPU or not. After choosing an adapter, you create a connection to it to perform operation, which is what we call a GPU device. And because I don't need any kind of specific feature there, I'll go with the default GPU device. Now, I want to draw some pixel on the screen, and for that, I simply need an HTML canvas element, as usual. So I'll configure the WebGPU canvas context with good default options, again, as we simply want to draw a red triangle. Because the GPU is a coprocessor that may not be on the same chip as the CPU, we must send those commands in batches. And for that, we use a builder object called the command encoder to add commands to execute on the GPU. Here, we simply tell the GPU to perform a render pass, then send all the recorded commands for execution. These commands consist of 2 programs, or shaders, that will be used to draw a triangle. The first one is a vertex shader, and it is responsible to position the vertices of the triangles on the screen. Here, the vertices are hard-coded, but in more complex applications, there could be tens of thousands of triangles and a lot of matrix math. The second program is called the pixel shader, and it decides on the color of each pixel. Here again, the shader is simple and only returns the color red. But real application would have a lot of computation to compute lightning or more. And because WebGPU is stateless, we have to encapsulate those shaders in a render pipeline. And with that, we instruct the GPU to draw 3 vertices for the triangle using that pipeline. And voila, we have a triangle, finally. Thanks to the power of the web, this triangle is now portable on all browser platforms with no effort. And to prove you that this code is actually working, let me show this triangle in a real browser. So I'll go to this simple demo page. First of all, there is a red triangle. And now if you go to the source tab, you can see the same code is there. No cheating here.
Okay, François, it's nice, but like I have a nicer triangle to show you.
Okay, thank you.
So this is a repository with C++ code in it. So if we look at the main file, we can see that it's basically the same red triangle, the code for the same red triangle, but in C++. So we can find common things like the shader here. We can find the encoder and the submission of commands to the queue, etc. The C++ file is 120, 130 lines of code. It's a bit longer because C++, of course, is a bit more verbose than JavaScript, and also because we have to do some window management here. We have a very simple build script as well. There's nothing to see here. And so if we build this, so it needs to reconfigure the build, there we go, and then execute the application, we can see the same triangle. And so what's interesting here is that this triangle will work on all desktop platforms, just like that, the same C++ code, same triangle on all desktop platforms. It's amazing.
Yeah, but I can share my triangle with a simple URL. Can you? Nope.
I can, actually. Let me show you. So to do this, we're going to use WebAssembly. So I'm going to switch to my WebAssembly branch. And the difference with the branch in native is very small. So we have some build system changes here, some window management changes here, and a render loop change. But like it's very minimal, about 20 lines. So we're going to build this. Again, there we go. And then serve this on the server and open the browser with it. And we get to see the same red triangle. It's on the web.
You stole my triangle.
No, it's not the same triangle. Let me show you. This is actually the C++ triangle, because if we go here using the DevTools, we can see that it loaded the C++ code through this WebAssembly application.
Whoa.
So the same C++ source code can run portably on all desktop operating systems and the web using WebAssembly. So, François, you see, this is because WebGPU is not just an API for JavaScript. WebGPU is a foundational brick, like WebAssembly, that has ramifications far beyond the web, thanks to a growing ecosystem. And again, the team at Google really sees this as more than web tech, but some growing ecosystem around the core technology. So let me give you a tour of this. Of course, the ecosystem starts with the JavaScript specification that you talked about, and again was a collaborative effort with a lot of organization, and the specification is either implemented or in progress in all the major browsers. But at the same time, Mozilla and Google believed in the potential of WebGPU in native and separated the WebGPU implementation from the browser so the library could be used on its own. So for Chrome, this library is a C++ library called Dawn, and it translates WebGPU calls to GPU driver commands. By using Dawn, C and C++ applications can use WebGPU in native as a portable and ergonomic GPU abstraction, and they also get to benefit from all the engineering of browser vendors. And so this is the path that was used to show the red triangle in native earlier. But what we also saw earlier is that it's very easy to bring a native WebGPU application to the web. Mscripten is the C++ WebAssembly toolchain, and it already has WebGPU support. So it's only a couple lines change to port your native application to the web. And that's the path that we use for the red triangle again. Okay, but now what if you have a JavaScript application on the web that you would like to take outside of the browser? Well, that's easy as well, for example, the Node.js JavaScript runtime has a WebGPU module based on Dawn, so you can run the same JavaScript code without modification, server-side or in other native contexts. And all of this is the C++ ecosystem around Dawn, which is Chrome's WebGPU library. But we have a similar ecosystem for Rust with WGPU, which is the library that Firefox uses for WebGPU. WGPU can be used directly by Rust applications, and then these applications can be ported to the web with WebSys, and likewise there's the Deno JavaScript runtime that supports WebGPU through WGPU. So this is very much a mirror ecosystem between the Rust world and the C++ world. So we have the JavaScript world with the browsers and the specification, we have C++ world, Rust world, but of course, maybe this can be your world, and any language could take advantage of WebGPU and may already have bindings for WebGPU. The engineers working on WebGPU implementations have been working on a common C header for the API native that can be used to target both Dawn, WGPU, Mscripten, and a lot of other things. So it's really easy to create bindings for any language using the CFFI. And we hope to see more of these bindings come over time.
So the question now is, how do you get started with WebGPU? I personally highly recommend a code lab called Your First WebGPU App. This will guide you step by step to build a game of life with WebGPU. If you want to learn more, samples are also a great way to approach some concepts like compute boys or shadow mapping or more. I must confess I spent too much time playing with those on my spare time. And finally, for native developers, check out this WebGPU cross-platform article. This will basically teach you how to build the red triangle Corentin showed us earlier, so that you can start building your own apps with WebGPU. Speaking of that, how about we play now a little game we called Where is WebGPU?
All right. Sure. So we'll present a bunch of projects or technologies, and please raise your hand if you think that WebGPU is in there in some way. So the first one we start with should be easy, and is WebGPU in TensorFlow.js. TensorFlow.js is the machine learning library in JavaScript.
Really? Come on.
Okay. So yes, you guessed it. WebGPU is very useful to accelerate machine learning workloads, and TensorFlow.js takes advantage of it. In the test, we had some machine learning models were 3 times faster using WebGPU than WebGL, and there's more improvements that we're thinking of, so it might get even better. So the WebGPU port of TensorFlow.js is already available there, and there's only a couple lines change you need to do to your application to take advantage of it. Next one.
Is WebGPU in 3.js, the most popular graphics library for JavaScript? Really, guys? Okay. And the answer is, there is a work in progress refactor of 3.js as we speak to use WebGPU. And this is quite far along, but it's not finished yet. So it's still possible to try it and start using compute shaders, like in the particle simulation demo you can see here.
All right, next one. Is WebGPU in Google Maps?
It's the most popular site today that uses WebGL.
And the answer, sadly, is no,
Sorry.
or not yet. Taking advantage of WebGPU can be a large effort because of how different it is from WebGL, and so it incurs some risk. So not all sites or libraries can be early adopters. But as the technology matures, we hope to see more and more uses of WebGPU as it becomes more stable and known. Yes. Next one.
Is WebGPU in Unity? Unity is a game engine often used to publish games on the web.
I see
2, 3, 4.
Oh, no, I see a bit more
5,
hands. Okay.
5. WebGPU support is in preview in Unity and can be turned on if in some configuration files. Like this screenshot, for instance, is from the Unity's demo bot attack project, and it's running in the browser using WebGPU at 120 frames per second. So that's impressive.
Is WebGPU in the JVM somehow?
0. Oh, 1, okay.
Okay, we have one person. And the answer is not really. So while we were making the slides, we looked into this and we saw that some people made a project called KGPU that added WebGPU bindings to the JVM, but it doesn't seem exactly complete. But in the future, we hope that we'll see WebGPU bindings in there, and actually the team working on Dawn is looking into that, so stay tuned. Is WebGPU in Cloudflare?
Cloudflare is a popular CDN service which has nothing to do with graphics.
Some hands, some people read Hacker News.
Yeah, 3 hands out of 1,000 people.
Well, it turns out it is. Cloudflare, so they have serverless workers based on JavaScript, and they just added WebGPU support to them using Dawn. And their suggestion in the blog post is that this could be used to do machine learning using the GPU on servers in response to some requests. And yeah, so right now, I think it would be a good time for questions. So if you have any questions, please ask me or...
I do have one question for you.
What?
Corentin. If GPUs are so great, according to you, why do we even have CPUs in the first place?
Okay, thank you. I'm glad you asked, François. This was definitely a space for your questions. So To do that, let's go see at what block diagram for a CPU looks like, so we can compare the two. Oh, so convenient, we have slides. So if we look at the CPU, there's like this is a very rough sketch of what the CPU core looks like. So we see a bunch of CPU cores linked to the RAM. In the CPU core, there's a very large control unit that decides which instructions to execute when. And comparatively, the arithmetic logic unit, the thing that does all the additions and stuff, is very small and has a small-ish number of registers. The reason for this is that the CPUs are optimized to run winding business logic or very much like serial code, but very fast. So what they have in the control unit is a lot of branch prediction, reordering, speculative execution, Spectre vulnerabilities, and whatnots. So that's for the core itself, and its link with the RAM is fast, but it is mostly optimized for latency. So maybe it's 100 gigabytes to access the 100 gigabytes per second to access the RAM, but that's it. If we look at the GPU instead, we also see an architecture that has multiple blocks that are copied multiple times, a bit like cores in the CPU. But inside the GPU block, we have a much smaller control unit with many more arithmetic and logic units. That means that the same instruction is going to be selected by the control unit for all the ALUs. They're all going to run the same instruction on different data because they all have their own sets of registers, and so that's SIMD execution. If we look at the link with the RAM, the bandwidth is much higher, but also latency is higher. That's fine because GPUs have hardware mechanisms to hide the memory latency. So it's fine. What we see here is that the GPU is optimized to run parallel workloads that have the same instructions but for different pieces of data. So CPUs and GPUs are optimized for different things, CPU for serial code and GPUs for parallel code. And that's why we have both.
Okay, I'll trust you.
Okay, so now if you have questions, please.
I do have another question.
Oh, come on.
If WebGPU is so great, why don't we use it to render the Chrome UI? Like, I mean, the buttons, the menu, everything.
Yes, I'm very glad you asked, François. This is actually something we're looking at. So again, to reframe your question, I think it's not, what François is asking is not can we render stuff in WebGPU in the browser, so like the triangle here, but also can we render all the menus, all the dev tools, and all that. So Chrome would be using Dawn for rendering everything, not just WebGPU. And it's something we're looking at. So if we go in about flags, so this is the config flags for experimental stuff in Chromium, we can see this option here. So this is the next generation of 2D rendering for the UI of Chrome and HTML and all of that. And they are looking to use Dawn, so the WebGPU library, as their graphics backend. Okay, we can't see shit there. So yes, they're looking to use Dawn as their graphics backend by default. And this way, they don't have to write a version of the rendering for each native API. This is currently trying to roll out on Mac, I think, but it's experimental in progress. But yes, that's it, François.
Thank you.
Okay, so now, thank you. François, no, please, if you have more questions, you go with the audience.
Okay.
There you go. So now it's time for your questions. Let me get back to the question slide. François, how many of these did you put? Come on. Okay, your questions for reals now. So if you have questions, please raise your hand, sir.
You showed that WebGPU implementation of, I think, TensorFlow was about 2 times as fast as WebGL.
Mm-hmm.
Could you explain a little bit why that happened?
Yes, so the question is, could you explain why the machine learning workloads can be faster, like 3x faster in the case of TensorFlow.js I mentioned, than WebGL, and why is that? The reason for this is twofold. The first one is that in WebGL, you have to pretend that you can use the GPU as a parallel machine that can be very flexible by drawing triangles. So literally, you have a neural network. When you have your neural net, there's a layer that's represented by a texture, and you draw a big triangle, and each pixel will have to look at the weights of all the things. But that means that adjacent pixels, they're going to have to load adjacent data in memory. But they can't share anything. So you kind of rely on the GPU caches to do a good enough job for you to gather all that data from memory. And so it's not always the most efficient. On the other side, compute shaders, you have a very explicit control over what happens and what memory loads happen. And also, yes, memory is most often the bottleneck in these memory accesses, is most often the bottleneck in these machine learning models. And so with compute shaders, you can group the work by tiles, and each tile will load memory cooperatively into some local memory next to the ALUs, so that they can access it much more efficiently, and you do explicit caching, which is much more efficient. There's other things that come later where you have the ALUs can share data between each other efficiently, and you can do partial sums and stuff, but that's a bit more advanced. Any other questions? No, François, you can have yours later. Sir? Did someone already port Doom to WebGPU? I'm not sure actually. It should be fairly easy to do so. I mean, probably. So some people have Doom in a completely in a fragment shade, in a pixel shader. So I think that version would be very easy to port to WebGPU, because you take the shader, you translate it to Wixel using some automated tooling, and that would just run. The engine itself would be doable with the WebAssembly flow I showed, but like as far as I know, no one has done it. It seems like you have your next weekend project. Okay, François?
If WebGPU is so great, like why do we still have HTML? Like if I can render everything in a canvas, for instance.
So yes, technically you can render everything on the canvas. So you could take whatever your Qt or whatever native application, port it to the web, and have all of that running WebGPU in a canvas. But the nice properties of the web and HTML, CSS is that the browser gets to see the structure of the content and can work with it. So for example, if you do your application only in WebGPU, you wouldn't get find in page, you wouldn't get accessibility options and screen readers, automatic dark mode wouldn't work, reader mode wouldn't work. Search engines would not be able to crawl your web page and find content, so it would not be very discoverable. And there's a lot more things like this. So like keyboard accessibility, like you can tab around form controls and stuff. So that's why WebGPU is not a replacement for HTML, CSS. It complements it for things that are either computations you need to do in your web page to do things, or more graphically demanding things. But just like an image tag, where it's a good practice to put an alt text on, it's a good practice to not just have a canvas, but also have text around it to explain what it does so that it's more accessible.
Thank you, Corentin.
Yes. How does WebGPU perform if you open a lot of tabs with WebGPU? So of course, all the tabs are going to share access to the GPU. As far as I know, Chrome will try to pace the frames of tabs that are not currently visible. So of course, these will consume less, unless JavaScript just keeps sending a lot of work and does not abide by this. But the access to the GPU is shared cooperatively between the tabs, meaning that it's not like we can preempt a tab to say, no, like you stop running, this one runs. That's not the thing we can do on GPUs, but they will share. I saw a question here, yes.
projection in time to for WebGPU to become the specification included into all browsers?
Okay, do we have an estimate of when WebGPU will be included in all browsers? So of course I can't speak for sure for other browsers, but I know Mozilla previously said in public forums they were hoping to do to have WebGPU in beta testing at the end of the year. In fact, today I think WebGPU is enabled if you use Firefox nightly. And Apple doesn't really share anything, but looking at the WebKit repository, we see that they're hammering on it right now, and like some of the samples we have that François linked to, the samples repository, actually work in Safari if you enable the correct developers options and stuff. But looking at the state of their code, they still have a lot of work to do, so I would count like at least a year of work for them to catch up.
I have a small follow-up question, if I may. Do you think WebGPU will enable web-based VR applications?
Will WebGPU enable web-based VR applications? So yes and no. So web-based VR applications are already possible. There's an API called WebXR where you can have where you can render things on headsets. It's used on the Quest, Meta Quest headsets, and more. I mean that's the one I have at home. So and so WebGL can do that and render it for WebXR. Because we're trying to get WebGPU out quickly, we didn't integrate with WebXR yet, but that's something that's coming soon. But in a sense, WebGPU is just a rendering API. So it will draw stuff to an image that will be put on the screen. The rest is more WebXR and the browser support for WebXR, etc. I saw, yes, a question there. Yes, sir. Okay, so is there some security concerns? Is the browser able to disable access to the WebGPU, and isn't there a concern about crypto mining using WebGPU? So the WebGPU specification is made so that it can be secure. That's like number one constraint from all W3C specifications. So as far like we use fuzzing, we have security audits on the implementation, etc. So the goal is that it's not exploitable for owning your machine, of course. Then there's the category of misuse called for abuse, which would be crypto mining. And in this case, we can't do much because it's very difficult to detect what is a valid, like, okay, let's run a heavy machine learning workload because the user actually wants something from the page versus crypto mining. So browsers can do a lot of things. They can prevent GPU access if they want, for example, for one-by-one iframes. They can prevent access in a bunch of other contexts, but also for specifically crypto mining of Bitcoin, say, WebGPU is not much more efficient than WebGL. The reason for this is that the compute shaders don't really add anything for this, and so the problem's already there. And like, if people really want to do crypto mining on your machine, they can use JavaScript or WebAssembly. So it's more something that the browsers will have to take intervention on by with things like safe browsing, which is the thing where you go on some sites and sometimes you have a big red banner that says this site is probably bad. Do you really want to go there, etc. Yes, you want to go on the bad site. Yes. Okay. Yes.
On the security perspective, are there also concerns between different tabs? Like if different tabs from different domains can access the same GPU, does that somehow?
Yeah, so is there a concern where multiple tabs from different origins can access the same GPU and could be potentially interacting with each other, snooping on each other, or stuff like this? That's definitely a concern, and so that's why, I mean, it's something we knew about, and from day one, it's something that WebGPU was designed to prevent. So for example, you could imagine that one tab allocates a texture, renders your bank account details in there, and then stops using that texture, and another site creates a texture and happens to get the data that was there. Obviously, we don't want that. So the WebGPU specification says that every single resource that is created must be filled with zeros. Of course, in the implementation, we optimize that to avoid doing the zeroing if we can, but we have a pretty insane number of tests that actually check that this thing is done correctly. And overall, like, I think we have like hundreds of thousands of tests now, fuzzing and a lot of things to try and make sure that all these security boundaries are implemented correctly. And so far, we haven't seen issues. Fingers crossed. Sir, and then sir in the back, and yes. Okay, so how is resource contention handled and like preemption, etc. So GPUs, contrary to CPUs, are not as good as at preemptive, like getting having an external signal that asks them to yield what they're doing so they can move on to a different processing. So most of the time, they will just keep running the thing until it's finished, and if it doesn't finish, then that's a problem. This is the role of the operating system. So on Windows, for example, if you do this, the operating system will notice that the GPU just never stops, and it will reboot the GPU. So you'll see a flash of black on your screen. Some applications that have data only on the GPU might lose it. But every application is supposed to handle what we call device loss like this. It could also be that you have an external GPU and that you unplug it. Chrome, in this instance, will notice that there was a device loss and will make a pretty good guess as to which website caused that. And it will deny GPU access to that website. Of course, not every operating system has this mechanism for recovering from a stuck GPU. And so on some of them, it's a bit worse and you might have to reboot the machine. But like in fact, this thing is, you can already get this thing in WebGL and even with CSS filters, like if you specify crazy filters that are super expensive, in some cases you can just kind of make your machine hang because we ask the GPU to do something that's too expensive and it just can't finish. So in a sense, denial of service like this is something that we know about. It's also very visible to the user. And so in terms of security, in our security principles, it's not something that we consider critical. It's bad and we try to avoid it, but it's not like someone is going to steal your data, is going to see stuff from another origin, etc. It's just denial of service that's very visible. You had a question. Okay, so the question is, does this completely replace WebGL, and is there some reason to keep using WebGL? And the answer is, WebGPU does not replace WebGL, it's a successor, but WebGL will, of course, stay in the web platform because one of the big philosophies of the web platform is that things work mostly forever, unless you use the blink tag. But today, there are reasons to use WebGL instead of WebGPU. For example, WebGPU is not shipped in the other browsers. Or even in Chrome, WebGPU requires support for compute shader, which some devices still might not have. It's a small fraction of devices, but still. In the future, let's say 5 years, I don't think there's any reason to use WebGL, unless you have an existing code base, of course. Because WebGPU is just more ergonomic, more efficient, more featureful, more supported. But today, there are reasons to use WebGL, of course. Sorry, at the back. how would you transition a WebGL code base to WebGPU? That's the $1,000 or more question. So,
2 lines of code, right?
huh?
Two lines of code change?
Okay, it's a 2-line code change. If you use a library that ported to WebGPU, and on the web, a lot of people use libraries for like 3JS, Babylon.js, TensorFlow.js, all the .js names, or Play Canvas. If you use one of these, transitioning to WebGPU is 2 lines of code potentially. If you are making one of these libraries, or if you have your own custom WebGL code, then it's a bunch more work, and I mean, let's face it, it's not easy. There's no easy solution. You have to start from like the ground up from your renderer and start drawing simple things and then implement more and more. And that's why, for example, when we talked about Google Maps having no WebGPU support, that's why not all applications can take the risk and the engineering cost of porting to WebGPU now. And I think you had a question, yes. Can you access other features of the GPU through, like hardware encoders, through WebGPU? And no, the WebGPU is only for the programmable part of the GPU, so the things that can run shaders and stuff. And even then, we don't expose all the functionality of the GPU, simply because it's very costly to specify and implement more and more features in WebGPU. We're doing so little by little, but we wanted to get something out first. So for example, something that you can't access right now is ray tracing. That's the new hotness in gaming, and WebGPU does not have support for that yet. No more. I was going to say, François, don't you have a question? I guess you have.
Yeah. So we said like we started this effort 6 years ago, but what took you 6 years to just have one specification? Like really? Did you meet like every 6 months or so?
Well, we actually met every week, or maybe sometimes even a bit more. So like making a web spec is very costly because you need to, and like, are we out of time? Almost. Making a web spec is very costly because you need to agree with other companies and organizations that have different views of the world than you have. But also, in the case of WebGPU, it's not just, okay, can we find an API that's ergonomic for JavaScript? We need to actually study what's possible on the various native APIs and try to find a common core that's also useful and easy to use, etc. And so that takes a lot of time. And then we had a bunch of delay as well because of the heated debate that you mentioned about the shading language, because that was probably the most difficult decision by far. In WebGPU, choosing what that language would be. And we got started on the language maybe 2-3 years ago. And so we had 2-3 years to build a new language, which is also, which is also fast in a sense. I mean, it's not fast if you make a language for your own use, but when it's a standard, then every decision is weighed a lot, maybe a bit too much sometimes. Maybe we can take one more question and then we're out of time and we can start discussing here and then move outside. Any last questions? Yes?
Why did you have to create a new shading language?
That was my question.
Yeah, he had this question as well. Why did we have to create a new shading language? So first of all, we can't use, shading languages are very different than regular languages because they can't do heap allocations. They have to be 100% inlineable. They need to have a lot of features they really need to compile easily to some assembly for a machine that's like kind of dumb compared to CPUs. So they have their own constraints. And then there were a lot of shading language that François described. To do it very quickly, GLSL is a standard, but it's in maintenance mode, and it's also a standard not done by W3C, so there was like difficulty making a W3C spec reference and use a Chronos shading language like this. HLSL is owned by Microsoft and didn't have a spec. And it's also like kind of a weird language. It grew organically, and so we couldn't use that. MSL, which is the one for metal, is C++ and is too powerful compared to what's possible to do on portably on all GPUs. Apple has this advantage that they know exactly which hardware they are targeting because it's their hardware plus whatever Intel, NVIDIA, AMD GPUs they have in Macs, in older Macs. And so these GPUs are all pretty powerful, and so they could go with a C++ type of language that would be not possible to run on, say, Windows computers or Android phones, etc. And finally, there's the SpearV language made by Chronos. This is not a human-readable language. It is a bytecode representation, a bit like LLVMIR. And this has multiple problems. It was first, it's like very hard to use because you're not going to write that by hand. So we would still need a language for people to write in. It's done by Chronos, which is another standards body, and so that was that. And also the semantics of it are pretty complex, and so making it portable was not entirely a given. So with all of that, we decided to go for a new shading language along with lots of tooling to help translating things left and right. And that's what the game industry and people using GPUs do nowadays. They all have pretty massive shader translation pipelines, and they use that. So overall, it's just like one more break in this translation pipeline they have to add. And with that, if you have more questions, we are going to stay around for a bit. Thank you everyone for coming, and I hope you had a good time.